Hello everyone, this is Dr. Rajesh, and in this lecture we will study the Gauss divergence theorem in three-dimensional, and this theorem was given by Carl Friedrich Gauss, and he lived from 1777 to 1855. He was a great mathematician. So in this lecture we will try to uh, have intuition of Gauss divergence theorem. For the same, let us consider a surface S, and this surface is a closed surface, and that surface is bounding the region R, and this is the vector field over the region. So this is the vector field over the region. So this is the vector field over the region. So, and if I say the normal to the surface is this one, this is the normal to the surface, and this is the vector field F over the region. Now, Gauss divergence theorem states that this surface integral of the normal component of the normal component of vector field over surface S. Here we will try to see the meaning of this particular integral. Say this is the field F, and its component in this direction is this one. So this gives the flux flowing out of the surface area. So this integral gives the net flux flowing out or in of the area. So I could say that this integral is giving the net change in the flux through the surface S along the normal direction. So this is the meaning, and for the same we have taken very small element. Say this is very small element ds, and when that small element added infinitesimally times, that gives the integral, and since it is a two-dimensional surface, so integral will be double integral. So this integral is giving the net change in the flux through the surface in the or along the normal direction. So this is the interpretation of this integral, and Gauss divergence theorem states that this integral is is equal to divergence of vector field F over the region R, and since it is volume integral, so here will be 3 integral. So now we will try to interpret the meaning of this one. We know that divergence of vector field gives the net flux, and over R means net flux through the region R. So this, if we take very infinitesimally small element in this region, say infinitesimally small volume element dV, so this is giving the net change in the flux over this small volume element dV in region R, and when these small volume elements are added infinitesimally, so this is giving the net change in the flux through the region R. So intuitively both are giving the same meaning. So hence the divergence theorem connects the surface integral with volume integral, and it is also a great tool to switch between the surface integral and volume integral. So if we say that divergence theorem is only applicable over the closed surfaces, divergence theorem is only for closed surfaces. Secondly, it gives an important tool to switch between the surface and volume integrals. So this is the divergence theorem. And now we will see what is the net flux in the particular case we have taken over here. Since this field is in this direction and normal is also this direction, so this component f dot n cap will be positive. Cos of 0 will be 1, so this will be positive. So this total flux is positive. So if I say that this total flux is positive, and if you see over here again, this normal in this case will be in this direction. Normal in this case will be in this direction. So again here the normal and the vector field both are in the same direction, so that will also be cos of 0 will again be 1, so this will be again positive. So if I say that this thing is again positive, so if I say that in this particular case that we have taken, the net flux is positive. So if I say that net flux in this case, net flux is positive, is positive. So in this case net flux is positive. So if we again see, this is the surface S and this is the region R, and this is the vector field. In this case this is the vector field. So this is the vector field. Now if we see this portion as normal is along this direction, this one, and here normal is in this direction. So if I say that in this case normal and vector field both are in same direction, so that will give the positive flux, that will give the positive flux. But in this case normal is in this direction and vector field is in this direction, so this will give the negative flux, this will give the negative flux. So since this figure is symmetrical figure, so we can think of it composing of two symmetrical parts. So the flux due to this part is positive, due to this part is negative, so positive negative and in equal amount are added, so this gives the 0 net flux. Net flux is 0 in this case. So now we take another uh, the last case. In this case let us say this is the surface S and this is the region R bounded by the surface, and this is the vector field, and the vector field in this is this one. So this is the vector field. So if we say the normal is in this direction and here normal is in this direction, so if we see that here this is opposite to the normal, so flux in this case will be negative, and in this portion also, since normal is in this direction and vector field is in this direction, so that is the vector field. So in this case, the flux will also be negative. So negative when added to negative, this is negative, this is negative. So net flux in this case is negative. Net flux in this case, net flux is negative. So that's all I have from this lecture. And if you like the lecture, please like, subscribe, share, and comment. This is Dr. Rajesh saying you goodbye. Take care. Bye bye. See you soon.